Huygens' principle states that a wavefront can be represented by an infinite number of point sources propagating outward with spherical wavefronts. These waves interfere and create a diffraction pattern. The constructive or destructive nature of the diffraction pattern is dependent on the optical path difference. Each Fresnel zone represents a half wave of defocus within the system. The optical path difference helps us determine the Fresnel number, which is inversely proportional to this L parameter, which helps define the system, and quadratically proportional to the aperture size.
Our Fresnel zones change as I adjust the aperture diameter.
Ooh.
And then they also change if I adjust the microscope translation. Except apparently it broke.
Shut up, Daniel.
In lab, the best focus was found by moving the microscope so that we are projecting our NF-2 and NF+2. Now the average of the distances represented the best focus position, and this is where we placed our microscope for the NF0 location in later data.
So in the part of the lab where we create a diffraction limited system, we assume that the micrometer has a 10 micron resolution, and we want to be able to take at least 20 measures across the area disk. So we need a 200 micron spot size. So we take that 200 micron spot size and we plug it into the diffraction limited area disk spot size equation and solve for the diameter. And so we got a diameter of 7.72 millimeters for our aperture. Then using that, we were able to find the F number of that system and then calculate the cutoff frequency. And then the inverse of the cutoff frequency was the slit width that we used for the MTF measurements. We put our slit at the best focus, which was somewhere around like here, and then we scanned this slit across, and then we moved it to the NF equals -2 and the NF equals 2, and we scanned it across in both, taking measurements on the power meter. The line spread function here, the MTF is this equation here, and if you look right here, we have our A sub C and A sub S, and those are written out here, and within those, this is the numerical approach, so we have these summations, and within these equations we have the AX, which is our line spread function. So you can see that we can go from our line spread function to our modulated transfer function, which is what we do in our MATLAB program. Here we have a PSF represented by this spot diagram. It's characterized by this H function. We take our slit aperture and we scan it across in intervals across the PSF. At each interval location, we integrate the number of rays falling within that aperture. When we do that for all of the intervals, we're left with this line spread function, which is characterized by this equation.
Our data was a little bit interesting. We used the MATLAB code provided to analyze the data. Here's the raw data for the NF0. Now we can look at the MTF and see that indeed our resolution is about 12 cycles per millimeter, as calculated earlier. Here's our line spread function, and here's our spread function, which is narrower than the theoretical. We move on. We expected to get NF3 for both of our measurements here, but we actually ended up getting, here's the raw data for NF+3, and we ended up also getting NF-5, which is probably an alignment error of some sort. Regardless, our MTF is still showing that we're getting 12 cycles per millimeter in both cases. Now here's the line spread function for the +3. Here's the line spread function for the -5, as well as the spread function for the -5, which is narrower, and the spread function for the +3.